Okay, today in class we're going to talk about functions. So what is a function? Well, a function is essentially like a machine. In math, function is a machine. Something goes into the machine does something to that thing, that's the input. We usually call the input X, and then whatever the machine does, it spits out an output, which we usually call Y. Okay? So for instance, one time I was teaching Math 60, and it was a Saturday class, 5 hours of math. Can you believe that? On one day. All right, well anyway, the student, she went to the vending machine. She put her money in, that's the input. Out pops the wrong kind of soda. She wanted a Coke, it gave her a Diet Coke. She didn't put any more money in the machine. She just kept pushing the button, and out was popping the wrong kind of Coke, the wrong kind of Coke, the wrong kind of Coke. So, what's happening with that machine? Is it functioning? Would you say it's not functioning? Yeah? Okay, the machine is broken. It's dysfunctional. If you put an input in, you expect to get one input out, not several outputs, right? What do you have to choose from? So I can also think of the input as like the question, and Y is the answer. Oops. So if the question is, what day is today? And you answer me that and you say, today is Monday. Oh wait, today is Tuesday. Oh wait, today is Thursday. You start giving me all these different answers. Then all of a sudden I'm like, how do I choose between what day it is? Because you gave me multiple answers. So every single input, in order for the machine to work and be functional, has to have exactly one output. Now, the output could always be the same output, but it just has to be one. Okay, so, and that's true of our relationships too. The reason why I bring up relationships is because in math we have this thing called a relation. A relation is just a set of ordered pairs. So a relation could be, 2, 3. That's an X, Y. Okay, it could be, it's a set, so I'm going to use set notation. Could be also 5, 6. 7, 8. Okay, I'm just making these up. This is what we call a relation because there's a set of ordered pairs. Now, is the relation functional? And you can think about this like your relationships too, right? Are the relationships in your life functional or not? So if I ask you a question and again, you tell me an answer, like think about maybe a little kid for a minute. Imagine you had a 2-year-old and you took the 2-year-old to the store and the 2-year-old says, hey, will you buy me this beautiful purple pen? And you're like, absolutely not. I don't have money for that. That's not in the budget. No. And then the child asks again and again and again. And so you start to wear down. And now your defenses are down. You're getting tired. You just want the kid to stop asking you. So what do? You change your mind and you say yes. What have you done to the child now? Oh, you taught the child that if they ask enough times and you say no, that eventually you're going to change your mind to yes. That is actually the definition of dysfunctional as well. Because you changed, the input was still the same, but you changed the output from from no to yes. So if you change your mind and you're not consistent, you're creating dysfunction, right? If we look at this relationship, if I say 2 is the question because that's my X, 3 was the answer. 5 was the question, 6 was the answer. 7 was the question, 8 was the answer. Notice that I'm not getting different answers for the same question. So that makes this relation a function. Okay, so that's just a little tiny bit about functions, but we're going to get into it more deeply. Some few real life examples. Any questions on that so far? So let's look at the definition here. It says a function is a rule that assigns to each number in the first collection, and that first collection is the input, or X, exactly one corresponding number to the second collection. The second collection or set is the output. Usually we call that y. And you might remember this from previous math classes, independent variable, dependent variable. That kind of comes into play as well. You can think of a function like a machine that accepts an input number, uses a number to process, or a rule, sorry, not a number, it uses a rule to process that number and produces exactly one output. Sometimes we might know what the rule is, and in this case, a rule could be an equation. It could also be a table of values. It could also be a graph, and we're going to look at all three of those different kinds. But here, if x is 4, that's our input. So my question would be, what the y value gives me, what y value corresponds to x is 4? When x is 4, what's y? And then, so what we do here is we put that 4 into the machine. That means we put it in to the y equals 2 times 4 plus 3. We get 8 plus 3. And that's 11, and that's where we get the y equals 11 from. So this one had a particular rule, and that would be evaluating an equation for a value of x. Now, I could put an infinite number of x values in, and I will get an infinite number of y values out. But notice, for every x value I put in, I'm only going to get one corresponding y value. And that means on the graph of y equals 2x plus 3, you would have the ordered pair 4, 11, right? You see that? That's x, y. So that's going to be a functional machine because it's only giving me one answer for every question. Does that make sense? All right. As a result, a function generates a set of ordered pairs. That's what I was just saying. Oh, it's funny how it says that. Okay, and that assigns each input value, or x, to exactly one y value. That's the output. So we have this thing called function notation. What's really convenient about function notation is function notation allows you to know what went into the machine. See, what happens here, when I put x into the equation, when I put that 4 in, the 4 basically disappears, right? Because I multiply it and then I add it. And so I don't have any record of what was put into the machine. But if I use function notation, if I use f of x, I would replace the y. Since I know that this is a function, I would replace the y with f of x. I would write f of x equals 2x plus 3. And that way, if I put the 4 in for x, I could retain it, and I would always know what was originally put into the function. Okay? So we call f of x function notation. The input is the x, and the output is the y. And we name the function f. So we say f of the input x equals an output y. All right, and so a lot of people look at this notation and they think it's really weird because they're like, well, does that mean f times x? And it really doesn't. It actually just means the function of x is equal to y. So we read it f of x, and it's not used for multiplication. So let's look at two examples of how we would use function notation. If we want to find f of negative or g of negative 3, now we can change this function to be called anything because I don't want to get it confused. We use f of x because that's f for function. But if I want to say, well, this was f of x and I have a different function, I can name it g of x or h of x. Sometimes if it's a word problem, we would use like c of x for cost or r of x for revenue, p of x for profit. You see, you get the idea. You can use a lot of different names for functions. So we go g of negative 3, and then wherever I see that x, I'm replacing it with the negative 3. Now, this is find, which is the same wording as evaluate. Evaluate means you have an x, and you're going to plug it in to find the y. So if we go ahead and do this, we get negative 6 plus 7. Negative 6 plus 7 is what? It's 1. And then what would that ordered pair look like? Negative 3 and 1. Now, does it matter? Could I put it the other way? Could I put it 1, negative 3? Why not? Right. So it's an ordered pair, and we always put the x first and the y second. Okay. Let's try this for what do we call that? H of x. H of x, and we want to find h of 3. Now, in chapter 12, which is the chapter after this, we're going to be getting into a lot of functions that look like this. Does anybody know what kind of function this is? It's a rational function, and we call it rational because the root word of rational is ratio, and a ratio is just like a fraction. So we have a fraction here. When you see variables in the denominator, you're going rational function. Actually, does anybody know what kind of function this one is here? Linear. And what about the function says that it's linear? Oh, very good. Y equals mx plus b form. We call that the slope-intercept form of an equation. What's the slope on this one? And what's the y-intercept? 7. So if I did g of 0, what's g of 0? 7. You didn't even have to really do very much math. That ordered pair is 0, 7. Does anybody know what special ordered pair that is? Y-intercept. Y-intercept. Okay, that has nothing to do with h of x. Let's switch colors. Keep it consistent here. We'll go h of 3. Now, what should I do with that 3 now that I'm plugging it in? That's my input. It's going to do what? Yes. All the x's get replaced with 3s. So we have 3 minus 3. And can you already predict what's going to happen? You have 6 plus 2, that's 8, over 0. What happens when I divide by 0? What's the answer there? It's undefined. Undefined. Okay? Because you cannot divide by 0. Think about this for a minute. If there was $8 sitting on the table and no one claimed it, how much would no one get? Well, no one can't take any money. What is there, a ghost in the room or something? No. No one can't come and take the money. So it doesn't actually, this question doesn't make sense. If I had $0 and I split it up with 8 people, how much would we each get? Here we actually get 0. So when you have 0 in the numerator, your answer is 0. When you have 0 in the denominator, your answer is undefined. And later on, we're going to look at the graph of this function. There's going to be a problem with using x is 0 because we don't, or x is 3, sorry. X is 3 is a problem, correct? Can we all agree on that? Okay, great. So note that in the previous problems, you evaluated for output numbers. In the following problems, you're going to solve. So the difference here is if it says f of x equals 20, that means I don't actually have the x value, right? I have the y value. So if it's asking me to solve means I don't have x, I only have y. So I'm going to take all of f of x and I'm going to set it equal to 20. 4x minus 8 equals 20. My goal is to find the x value that gave me y is 20. So what was the question? The answer was 20. What was the original question, right? I'm going to work backwards. How can we solve for x now? We want to solve. Add 8. I heard add 8 to both sides because we're just trying to isolate x. So I get 4x equals 28. What next? Divide it by 4 and I get x equals 7. So that means my solution, and if I solve, then I can use set notation. We call this set notation. Okay, and my solution was 7. So if I were to check this, I would go f of 7 should give me 20. If I plug in 4 times 7 minus 8, I get 28 minus 8, which is 20. So that worked out. So that's my check. I say, well, if x is 7, does it give me the original number back. Okay? Let's try it. Now, this was what kind of function here? Linear function. What's the slope? Because I was pointing to it, right? I was trying to trick you. 4 is the slope, and what's negative 8? The y-intercept. If you were to replace x equals 0, you would get negative 8. 0, negative 8 would be the y-intercept. Let's look at it here. Now, when you look at this function is called g of x. Is this a linear function? Is that going to graph a line? What's it going to graph? Parabola. Because how do you know? What about the function says, I will graph a parabola? Yes. Where are you seeing the quadratic? Yeah, the x squared. X squared makes it a quadratic. So if we go that's not g. No, actually, we're not doing that. We're setting it equal to 5, I don't have the x. So what do I have to write? In order to solve, what should I write? Tell me what to write. I want to solve, what's that? Equals 5. Brilliant. Okay, what should I do now to solve this? Isolate the x. Okay, I'm gonna suggest there's a lot of different ways we could solve this. You could isolate x squared, but that's not going to work for all of your quadratics. So what I'm going to say, since we did all this factoring, let's set it up to factor. How would you set it up to factor? You always want to solve a quadratic by setting it equal to 0. I love it. Resounding 0. So I'm going to subtract 5 from both sides. X squared minus 1 equals 0. How do I solve that for x? By factoring. How do I factor that? Because we call this one difference of two squares. And so you end up getting, when you solve this, you would have x plus 1 equals 0, x minus 1 equals 0, minus 1, x equals negative 1, and plus 1, x equals 1. So our solution set, we have two numbers, and I'm sorry I kind of made a mess here. So my solution set is negative 1, 1. Okay, now some of you were wanting me to isolate x, and that would have actually worked too. I'm looking for a piece of scrap paper so I can show you that. If we had isolated x, we would have had x squared plus 4 equals 5. We could minus 4. We get x squared equals 1. Well, what a lot of people will forget when they do it that way, right? This is just another way to solve the problem. If I isolated x squared, I would take the square root, but I would get x equals plus or minus 1. Most people will forget both. That's why I'm suggesting solve it by factoring so you make sure you get both. Does that make sense? Questions about that? Here, I'll put that back up. That's another, we call that was from Math 65, we call that the square root method. But it doesn't work for all quadratics. So that's why I kind of wanted to show you the factoring method. Okay, any last questions before we finish that up?